Okay, so now that we've seen the polysynth device, we have a better idea of what makes a subtractive synthesizer tick. Now, what I'd like to do is start to create something similar ourselves using the Polygrid device. With the Polygrid, we can take individual modules and connect them however we see fit, and this will be a great way to start learning about synthesis. So let's go to track 2 here. I have a Polygrid device already loaded, and I want to expand it, so I'll just click this button, and this is what's inside. Now, with the Polygrid device, by default, it's set up to operate like a synthesizer. We see over here, I have something that says triangle. This is an oscillator. When it comes to synthesis, the sound generally starts from an oscillator. And the purpose of an oscillator is to generate a certain waveform and make that waveform cycle a certain number of times per second. How many times this waveform cycles per second is known as the frequency. The frequency is generally denoted by the term hertz. Okay, hertz meaning wave cycles per second. So all this is very relevant, and we'll dive a bit more into this right now. This particular oscillator is generating a waveform known as a triangle. And this is what the waveform looks like. All right, it's an upside down triangle. Now, depending on the shape of the waveform, this is going to influence the sonic characteristics of the sound, the timbre of the sound. So let's go ahead. I'm going to add up here, it says display. I'm going to find something so we can actually visually see what's happening as I play notes with this oscillator. So I'm going to use an oscilloscope. I'm going to connect the output of my oscillator to the input of the oscilloscope here so we can actually see what happens with this waveform. And we're going to play some notes. Let me move this over here, and there we go. Okay. So again, the waveform right now is generating a triangle. This is what the shape looks like. Inside of this box, I see one complete wave cycle of the triangle. All right. It starts low, at the midpoint, goes up to the top, and then again goes low. And just to re-emphasize this, we cycle through this a certain number of times per second. Based on how many times per second we cycle through this waveform, that determines the frequency, which is directly tied to pitch. If I start to play notes with this, inside of the oscilloscope, based on the note that I just played, it's making this triangle waveform cycle a certain number of times per second. As I play higher pitches, we're going to see more triangles fit into this oscilloscope, which basically means that it's playing at a higher frequency. All right, we're generating more of these triangles per second. Couldn't see my keyboard for a bit. Now, if I jump up an octave, we'll really see the difference. All right, so again, we're generating more of these per second, the frequency, all right? The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. Now, in terms of the actual sound of this, the timbre, that's influenced by the shape of the waveform. Now, we have a few controls here where we can alter the shape, which will just give you a good example of how the shape of the waveform influences the timbre. So I'm going to use this skew parameter here as I hold the note. And what we're doing is we're changing this triangle into something that looks more like a sawtooth, which is very, very bright, as you can hear. So we can go from an upward sawtooth or a downward sawtooth, or keep it in the middle for a triangle. We also have this fold parameter here. Where we can basically generate even more triangles by folding and manipulating this shape. So all of these controls exist on the oscillator level and allow us to change the timbre of the sound and also to change the frequency of the tone being generated. Just remember, frequency is directly tied to pitch. The higher the frequency, the higher the perceived pitch. The lower the frequency, the lower the perceived pitch.